Let's use Kirchhoff's loop rule for inductors to investigate the current behavior in circuits that contain inductors. Generally, we include inductors in circuits if we want to prevent rapid changes in current. Apparently, inductors are helpful if steady current is desired in systems with fluctuating voltage source. A circuit that contains a resistor and an inductor is called an RL circuit. A resistor is described by its resistance and an inductor is described by its self-inductance. When this switch is closed, the current flowing through the circuit increases rapidly until it reaches a steady value. Let's use Kirchhoff's loop rule to derive an expression for the current. So starting here, we have, since this offers a potential rise, this is positive. So assuming that the current flows this way, if you forgot how we choose the direction of current initially when using Kirchhoff's loop rule, please watch my lecture on Kirchhoff's rules. The link is in the description box below. When our imaginary loop passes through this resistor results of a potential drop. And finally, when our loop reaches this inductor, this is actually negative L di over dt. Then closing the loop, this is equal to 0. Recall that from our Kirchhoff's loop rule for inductors, when you have an increasing current, the potential across the inductor is negative. So this is our working equation, and I like to derive an expression for the time evolution of the current in this circuit. So solving this differential equation in terms of current, then I'll multiply both sides with R. I'll multiply this with 1. So I'll integrate this from 0 value of current to a value of I, and this one from time equals 0 to t. So notice that the exponent from this equation has an argument of negative R over L times time. In RL circuits, we have this concept of time constant and it is equal to L over R. Now it is arranged this way instead of R over L so that when L is large, the time constant is large and hence the slower for the current to increase to a steady value. So when it is arranged this way, it gives us a clearer picture that when the self-inductance is large, then it takes longer time for the current to reach a steady value. Now let's go back to the figure. When the circuit reaches a steady current, at this instant, we remove the EMF but let the current flow throughout the circuit. So essentially, I'm just going to remove this while the entire circuit is in steady current. So this time, I'm going to remove the EMF while the entire circuit has a steady current. So it happens in a split second. When I remove the EMF while the entire circuit has a steady current, the current decreases over time, and the decrease in current doesn't happen immediately because of the inductor. Remember that the purpose of inductor is to resist rapid changes in current. So gradually, the steady current will die down from an initial value, for example, I sub 0 to 0. So let's derive an expression for the time evolution of the current when we have this circuit. So if I try to write down the Kirchhoff's loop rule for this circuit, I have negative IR minus L di over dt equals 0. Notice that the sign here is negative even if the current is decreasing. This is because the inductor expels energy to reduce the rapid change of the current in the system. So this time, we don't have an EMF. I'll integrate this from an initial steady current of I sub 0 to 0 because there's no EMF driving the current. So eventually, the current will become 0. And this is evaluated from time equals 0 to t. And this is our expression for current when we have just a resistor and an inductor in a circuit with an initial current, I sub 0. Let's now investigate the behavior of a circuit if it contains an inductor and a capacitor. So consider this capacitor and we assume that initially it is fully charged and one plate has a charge of positive Q and the other plate has a charge of negative Q. So if we have an inductor and we suddenly connect it with our capacitor, the capacitor will begin discharging. We can imagine that it's pushing all the charges this way. So I can assume that the current passes through the inductor this way. Now let us use Kirchhoff's loop rule to derive an expression for the behavior of the circuit, and I'll just assume that my imaginary loop goes this way. So writing down, we have a potential drop at the capacitor and another drop in the inductor, and this is equal to 0. This is negative even if the capacitor is the one initially driving the current. This is because no EMF is included or connected through the circuit, and therefore it is the capacitor that loses its electric field energy to drive the charges in the circuit. So that's why this is negative. And obviously, this is negative since there is an increasing current while the capacitor discharges. So this is based on our previous Kirchhoff's loop rule for inductor. So based on the definition of capacitance, this is equal to Q over C, and then this is negative L di dt of 0. So recall that definition of current is I equals dq over dt, so I can plug this here. If we examine this equation, let Q equal f of x, and if we get the first time derivative of Q, we have g of x. And this equation tells us that when we get the second time derivative of Q, based on this equation, we end up with the same function, but this time it is multiplied with a negative constant. So apparently this behavior is depicted by either an exponential function or a trigonometric function. So to solve this equation, let's assume that Q of t is equal to a trigonometric function like cosine omega t. So if I get the first time derivative, it is equal to negative sine omega t times omega. And then when I obtain the second time derivative of q, the derivative of sine is cosine, so I'll have negative cosine omega t times the argument. And using chain rule, we have to multiply this with omega, which tells us that this is equal to negative omega squared cosine omega t. This is consistent with the fact that if we get the second time derivative of q, we obtain the same function, but this time it is multiplied with a negative constant, which is similar to this structure. So this is actually a valid solution. if we assume that omega is equal to square root of 1 over LC. So just like solving any differential equations, when we are given initial boundary conditions, we can actually calculate for the values of the amplitude. So generally, this can be written as Q of t equals cosine. This must have an amplitude. And let's represent this amplitude with Q omega t plus a phase angle. So again, this can be obtained if we have initial boundary conditions or initial values. But in an RC circuit, we are sure that the omega here is the angular frequency of the circuit. We usually have a value for angular frequency for systems that are oscillating. So in our case, this is actually an oscillating circuit because when the capacitor discharges, it will produce a current that passes through the inductor. But by the time that this system reaches a steady current, it already produces a magnetic field inside it. And remember that when you have a fluctuating magnetic flux, since the current is changing over time, this produces a back EMF, and such EMF will resist or oppose the change in current. So by the time the capacitor is completely discharged and the current in this inductor has a constant current, the magnetic field will then produce an induced EMF, and this induced EMF will push the current in such a way it will continue charging the capacitor in the opposite direction. So when the capacitor is completely discharged, there is a magnetic field here that will produce an induced EMF, and this induced EMF will continue to push the charges in this direction. So after some time, this plate will acquire a positive charge and this plate will acquire a negative charge. And once this is fully charged and the magnetic field loses all of its energy in pushing the current in this direction, then the capacitor will begin discharging in this direction until it repeats the cycle. So actually, this circuit produces an oscillation, and its angular frequency is given by this expression. Let's include a resistor to our LC circuit because in reality, any circuit experiences some form of resistance. Using the same reasoning from our previous derivations, we end up with this working equation. So initially, this capacitor is fully charged using the Kirchhoff's loop rule. So I'll multiply both sides of the equation with negative 1 over L to get rid of the L here. Recall that the definition of current is dq over dt. So I'll replace all current here with this definition. Now for easier notation, let alpha equals R over L and beta equals 1 over LC. So I can rewrite this in a shorter way, which is Q double prime plus alpha Q prime plus beta Q equals 0. So there are general ways to get the solutions of this equation. This equation is actually a second order homogeneous differential equation. Let me try one method. So recall that an exponential function has derivatives that are multiples of itself. So such function will have a form similar to our equation if we take its first and second derivative. Therefore, let's begin with q equals e raised to xt, and if we try to calculate q prime, we have x e raised to xt, and if we try to calculate q double prime, we have x squared e raised to xt. So let me plug this expression in our equation. So I have x squared e raised to xt plus alpha x e raised to xt plus beta e raised to xt equals 0. So I'll factor out the common terms here. I'll end up with x squared plus alpha x plus beta multiplied to e raised to xt equals 0. So since this must not equal to 0, otherwise we will not have a non-zero solution from our assumption. So the only thing that will make this equation equal to 0 is that this factor is equal to 0. We can now calculate for the value of x so that we can plug it back here. So using quadratic formula, notice that this equation is in the form of ax squared plus bx plus c equals 0. And using quadratic formula, it has a root that is equal to negative b plus minus square root of b squared over 4ac divided by 2a. Notice that in the quadratic formula, the square root sign can be positive or negative. So essentially, we have two roots. One is for a positive radical sign, which is negative alpha plus alpha squared minus 4b divided by 2 times 1. There's no 1 here. Then the other root, we will be considering the negative sign. Negative alpha minus square root of alpha squared minus 4 beta divided by 2. So if alpha squared minus 4 beta, meaning to say the term inside the square root sign, is greater than 0, then we have a real solution, and apparently the solution consists of exponential function with the roots given by these two roots. So we have 2 plus some constant if we have initial boundary condition or initial values. Otherwise, if this term is negative, then this term will generate a complex number. So essentially, these two roots will be in the form of a complex number. And recall that a complex number has this form with a real number and an imaginary number. When this factor generates a complex number, we now write this in the form of, Q equals EAT for this factor, and then here, instead of writing this in exponential form, we use Euler's formula and just consider the real term. So remember that Euler's formula is like E is e raised to I theta equals cosine theta plus I sine theta. So we will just consider the real term and multiply it with this function. So we have cosine this value bt. So if we have initial boundary conditions or initial values, we can determine the constant factor here. I leave it as an exercise for you to plug the necessary variables. Remember that these are composed of alpha, beta that are equal to these variables, and you may just plug it here. And that would be the solution of this expression. When you derive the solution of this equation, you will have two cases of solution. The first one is underdamped harmonic motion. When we say harmonic motion, it is a motion that has a restoring force, and this restoring force is proportional to the displacement. That's why usually harmonic motion has a form of an exponential function or a trigonometric function like sine or cosine, because there is a periodicity in the motion. And remember that from earlier discussion, when we have this LC circuit, this actually generates an oscillatory motion. So when you have an underdamped harmonic motion, the value of R results to a gradual damping of oscillation. So for example, if this is your axis for the amount of charge and this is the axis for time, and this is a maximum amount of charge that a component can have. When you have an underdamped harmonic motion because of the presence of resistor, eventually the accumulation of charge in a component oscillates this way and eventually it will die down because of the presence of the resistor. Another possible solution of this equation results to what we called overdamped harmonic motion. So this happens when the value of your resistance is extremely large and it results to a system that is already damped even before it begins oscillating. So for example, this axis is your charge and this x-axis refers to the time. The accumulation of charge in any component dies down rapidly even before the entire system has a chance to oscillate. Don't forget to like this video, subscribe to my YouTube channel, and hit the notification bell button for awesome updates. Thank you for watching!